Perfect. Now we do some numerical experiments to show the goodness of our approach in reconstructing function with discontinuities. This is the main results that I hope that everybody understood after this presentation. So we start with the first, so we have 3 experiments mainly. So we started from the first one. The first one is a typical experiment coming from medical literature in some sense, because you see, there are 2 phantoms that are used for imaging analysis in a broad way. So the first one is called the Shepp-Logan phantom. This is called a geometric phantom. And then there are 2 discretizations that we take into account. One is obtained using the so-called Lissajous nodes that I explain in a bit what they are. And the other are the Lissajous nodes, let's say, of lower cardinality. What are these Lissajous nodes? Lissajous nodes are points that are sampled on Lissajous curves. Lissajous curves are space-filling curves of a given domain. In this case, the domain is the square minus 1, 1 to the square. Okay. And these points, as you see, they accumulate mainly on the boundary, on the corners, like the so-called Chebyshev points that accumulate on the boundary, and that for interpolation usually are very good, allowing to reduce interpolation error because the Lebesgue constant grows in a logarithmic way. And these points has a similar property, and what are important, which is important is that can be defined in every dimensions. This notation LS2, 2 stands for the dimension of the space where we were working, and 32, 33, these numbers are related to the way in which we sample the points by using a scanner. Actually, for the scanner that we use, this is the highest dimensions, and the dimension of these points are essentially 32 plus 1 times 33 plus 2 divided by 2, which is a little bit bigger than the dimension of the polynomial space of the corresponding degree. Okay. But for details, there are plenty of papers that present the Lissajous nodes in every dimensions. But they are important for the type of application we have in mind. So the first test was the following. So we use this Shepp-Logan, so this phantom here, which we call f of SL, which is an object that stays in minus 1, 1 square. So the function FSL is defined as the composition of 10 step functions. In fact, there are 10 ellipses inside here. Okay. So a discretization of this FL on an equidistant grid, which is made by 150 times 150 points, is displayed above on the left. So this is a discretization on our phantom using this grid. So the experiment was done in the following way. So we increase n in this way, using this so 4, 8, 12 up to 40. And so we interpolate the Shepp-Logan function at the Lissajous nodes defined in this way. And as kernels for our RBF interpolation, we use this maternal kernel and the Gaussian kernel. So C0, C2, and C4 are the different type of smoothness of the maternal kernel. The Gaussian is infinity, has infinity smoothness. So we computed the RBF as well the VSDK interpolant for all sets of Lissajous nodes. Then we put in a diagram log the plot of the field distances against the L2 error between the original shape log and the interpolant. As an approximation of the continuous L2 error, we use the root mean square error. As a scaling function, we use this function psi of x, which is 1/2 this shape log function. So a scaling function with the correct a priori information of the discontinuity. And so in the next figure, we display this log diagram, the slope of the regression line that we have in a table, one that I put later here. Here is the slope of the, but as you see here, the convergence rate for the VSDK is much bigger than the convergence rate for the RBF interpolant, which, as you see from the picture, they are concentrated between, let's say, minus 0.8 to minus 1. Here we are going to, you say, minus 6.5 up to minus 3, which is the power actually of the convergence that we are indeed showing with the different kernels and different color indicated here. Here you see in the table, as I already said, the slope of the VSDK convergent and the slope of the RBF using the different kernel. Why the slope of the VSDK are much better? The reason is in this, let's say, in this explanation that the slope of the regression line for the RBF interpolation is for all four kernels between 0.25 and 0.31. The low order, because the Sobolev space corresponding of the shape log function is the following one with 4s less than 1/2. On the other one, if we use this psi, so it's increase the smoothness of the Sobolev space, which become of this 4 for s bigger than 0. And thus, as predicted by the theory, the convergence rates are determined by the smoothness small s of the applied kernel. And so we get a much better. This shows that if we are in the proper Sobolev space, then we can approximate our function in a better way. And this is exactly the answer that is given in this result, in this first experiment. The results here are clear because, as you see, this is the VSDK interpolant obtained using the Lissajous nodes 4041, which is the last in the experiments that we have obtained. And this is what we get simply using the RBF interpolant. So there is a very poor reconstruction of our shape log. And so the VSDK scheme is much better performing if the scaling function is known a priori. But now, in the second, there is another example here, simple example that show visually using not Lissajous points, but using, for example, these Alton points. The Alton point, as I said, are points with low discrepancy, which are quasi-uniformly distributed and can be defined in every dimension. Okay, so in this case we take 17 to the square Alton points on omega. Omega is minus 1 to the square, and the grid mesh size is of this value here. So we interpolate the function via the classical RBF on the set of nodes using the Gaussian kernel. selecting also the optimal shape parameter using the leave one out cross validation. But if we use the scaling function, we use the strategy as before, so we have this VSDK, or now the VSDK based on this scaling function, and the result is clear that the result is much better using the VSDK for the reconstruction of this function, which is actually a kind of sphere. Is a kind of sphere in the square. Okay. The kernel that we use in this experiment is again the maternal kernel, the C0, if I remember well. So the problem, as I said, is that we need to extract the discontinuity in some way. Well, there is a machine learning approach for this extraction, and this is based on a segmentation by classifications. So we use algorithms from machine learning to obtain a segmentation of the domain by classification. And we focus on the support vector machine. Why the support vector machine? Because they can be applied directly to scattered data, which is exactly the setting which we are working with. That's why it's important to use this approach. So now, the segmentation by classification, the basic idea is the following: to obtain a classification of our omega, which is indeed an image. Indeed, it is an image. You think a function, but it is an image. We separate the values so that we sample our image in n classes that we call S1 and Sn, so that all the nodes in one class, let's say Sj, are precisely contained in omega j. Then we link every class to a value alpha j, which is a real value, and then we label and set the label z I equal psi of xi is equal to alpha j if the points is contained in Sj, in the class Sj. From the labels of the point in the set X, we derive a classification for every point X in the domain omega. So, the support vector machine, as I already claimed, is the computational tool that we use for doing the required classifications. If you want to have more details about that, look to the paper that I have already mentioned before in SciEM Journal of Scientific Computing of this year. Okay, so the reconstruction algorithm, once we are able to classify our function or image, is something that we can call not data-driven, but shape-driven interpolation with the discontinuous kernel. So the input of the problem are the nodes, obviously, in which we sample our, and the corresponding values f. Then what we get as output is the VSDK interpolant at every point x of the domain omega. So the first step consists in extracting the label z, the set big Z for x, using the values f with the classification strategy outlined before. Then we train the kernel machine with the points x and the label z to obtain a prediction of the scaling function, because in general now we don't know the scaling function, but we want to get a prediction. Now we calculate the coefficient, so we solve the interpolation problem with the VSDK based on this scaling function predicted using this strategy. And then we evaluate the interpolant at every point x of the domain omega. This is the reconstruction algorithm that now we know, the one that we have used. So the third example is the following one. We consider now the geometric phantom, because we showed before there are two phantoms. So this is the geometric one that interpolate on this Lissajous set now, and then we use again the ordinary RBF interpolation, the VSDK interpolation, but using the C0 matern function. So on the left you see the comparison of the RBF interpolation on the left with the VSDK scheme. So this is the RBF and this is the VSDK. And this shows also the, let's say, the boundaries obtained using the RBF and the one obtained using the approach described in this part. So, comments about this example. This example, we have these comments in the sense that we compute the relative L1 errors of the two reconstructions. Actually, these two errors are the relative ones. And then you see that the one that we obtain using the VSDK is slightly better because all the consideration that we have done before. But now the difference is not much bigger because we are predicting the discontinuity. We don't know exactly where they are. We are predicting using this support vector machine approach. But we want to point out once more that in the case the discontinuity are not known a priori, the VSK interpolation strongly depends on the performance of the edge detector. So if the edge detector is not, let's say, optimal or is not the best, then the VSDK reconstruction is poorer than the one that we expected if we know exactly where the jumps are located. So the final application is the so-called application to the magnetic particle imaging. So what is the magnetic particle imaging? Well, is a new quantitative imaging method invented in the early of the century by Gleich and Weizsäcker at the Philips Research Laboratory in Hamburg. The idea behind the MPI is a tracer that consists of a super paramagnetic iron oxide nanoparticle injected in the body and then detected through the superimposition of different magnetic fields. I show in the next slide a picture of a scanner, a typical MPI scanner. Common MPI scanner, or in common, they have the acquisition of the signal is performing following a generate field free points along a sampling trajectory, and the trajectory is a Lissajous curve. Now we know why the Lissajous points, which discretize the Lissajous curves, are important in applications, especially for image reconstruction, because they have found a very useful setting in this MPI reconstruction. To reduce the amount of calibration measurement, the reconstruction can be restricted to particular sampling point instead of curves, as I already noticed, along what they are called Lissajous curves. And the definition of Lissajous nodes is introduced above, but it is essentially what we have already seen. Okay. Among Lissajous curves, there are Padua points, the Lissajous points, there are the Padua points, which are a particular set of two-dimensional points on the square. They are particular because they are quasi-optimal for polynomial interpolation of total degree less than or equal than n, because they have the Lebesgue constant that grows like log square n, which is the best that you can get in two dimensions. But unfortunately, the Padua points are known only on the square, but not in higher dimensions. So, About the MPI scanner, I show two different types of scanner. One is obtained by using a cylindrical bore. The other one is obtained by using a single side scanner. It's called a single-sided scanner. So there is only two magnetic, let's say, ring, one into the other. And one is the receiving signal, the other one is the producing the magnetic field. So here you see the results that you can get using this kind of scanner for humans. Unfortunately, so far these scanners are not working for humans, but for animals. And then you see this Bruker one can be used only for a small animal or piece of our body. But the scanner for the total human body are still on the way. So the final example that we have tested is exactly for an MPI application. So as a tested data, we consider MPI measurement conducted on a phantom that consisted on 3 tubes filled with a special contrast agent called ResoVist. Okay, so the reconstruction of the particle density is on the Lissajous nodes, 33, 32. This reduces reconstruction on the Lissajous nodes as illustrated below. Then, as a reference solution, we compute a polynomial interpolation of the data where ringing artifacts are visible. In order to obtain the labeling for the classification algorithm, we use the simple thresholding strategy described above, using 1/5 of the maximal signal strength as a threshold for the binary classification for this example. And so the scaling function psi used for the VSDK approximation is obtained by using the classification algorithm that we described before, using the Gaussian function in this case. And so the results are clear that you see what happened. So on the left, you get the data on the Lissajous nodes. Okay, this is what you get, and the reconstruction obtained using that. But if we know exactly by the classification algorithm where there are the discontinuity, then on the right we have the result obtained using our technique, using the VSDK approach, and visibly the result is much nicer. But you can confirm this also from using many indicators like the SSIM, the structural similarity, or other indicator for image analysis. So I conclude just putting some references. As I said, it's just a page of references that people can take into account just for understanding better what I have seen so far. But there is some more, if you like. I have some lecture notes that I have written during the past years, in which you can understand many of the details that I left in this presentation because of the sake of limitation of time, of course. And this lecture will be done using with my postdoc Emma Perracchione. And here you see there are many chapters in which I describe also what are these discontinuous kernel, and also the machine learning, which is the topic that people are interested in this workshop. So my thanks to the organizer, and I special thank you that I wanted to conclude is to the Rete Italiana di Approssimazione, RITA, which is the network that is grouping together all the people working approximation theory, and also a special thank you to the kernel group, which is a European, no European, is a worldwide group of people working in kernel approximation that I be taking part since the beginning. Thank you very much, and I hope to be in touch with someone interested on this topic.